All right, almost forgot. Parametric equations. So parametric equations, they describe the path of a particle. Yeah, sorry. Along a curve. So, you will see them written in one of two ways. We could say something like C of t equals x of t, y of t, and it's written like a coordinate pair. And it'll make sense when I show you the very first example, which is coming up, what that means. Or you might just see it written as x equals one function, y equals another function. T is often used as, T is called the parameter. And T is often used because it's often in terms of time, but theta is another common one that's used as a parameter because for angles. All of that will become clear in a moment. So, let's look at an actual example and see what the heck is meant by that. Example. Sketch the curve. Described by the parametric equations x equals t squared minus 4, y equals t over 2 for negative 2 less than or equal to t less than or equal to 3. Boom. So I'll let you guys get caught up with the writing, and then we'll see what we do here. Anybody happen to remember, I mean, I wasn't back there with you guys back in the day when you first learned how to graph functions, but I'm guessing you all probably learned the same strategy. Anybody remember what the first strategy was you learned for graphing a function, like graphing a line? How many of you guys do you think started with making a table? No? No table? Never ever. You don't even know what I'm talking about. What the heck is a table? We're going to make a table. All right, does anybody need the cloud? All right, cloud's going away. It's a sunny day now. Let's make a table, but we're going to make a table not with 2 columns. 3! And actually, it's going to be rows because I feel like being difficult. So we're going to make our first row be t, and the next one be x, and the next one be y. You could make them columns. I just am going sideways. And it says t is between negative 2 and 3. I'm going to just pick whole numbers between negative 2 and 3. That's going to give us quite a few values. Let's see if that gives us enough to see what's going on here. We'll put some extra values in if we need them. And we literally just plug in the numbers into x and y. So when t is negative 2, x is negative 2 squared minus 4. That'd be 0. Whoops. 0. I'm going to keep going on the x's. When x is negative 1, we get 1 minus 4. That's negative 3. When x is 0, or t is 0, x is negative 4. When x is 1, it's back to negative 3, back to 0. 9 minus 4 is 5. Any questions where I'm getting those numbers from? Fill in the y's. Let's do those. Yes.
Isn't that a 1, not a 2? For the 1?
I was just seeing if you were paying attention. That's a good job. Well done. All right, so now what we do is these are just x, y coordinates, which is why in the cloud, when I said one of the ways you'll see parametric equations described, you have an x coordinate and a y coordinate, and we calculate those x and y coordinates by having some value of t that we plug in. So we have a whole bunch of points now, so let's go ahead and plot them. Let's see here. We got x has to go from -4 to 5. Y doesn't have to go very far. I'm going to make a wide but short graph. I'll make my scale 1. Both axes. And then we just plot the points. So the first point is 0, -1. The next point is -3, -1/2, -4, 0. Oh, that's where I was. -3, 1/2, 0, 1, 5, 1, 2, 3, 4, 5, 3/2. And so can you see the shape? It's a parabola on its side. Now, here's the thing though. This is what's going to make it a little different. When t was the smallest value, we started at this bottom point and we traveled along this path and then stop. We're not going to extend them with arrows. We're going to stop because there's a specific start and stop point for t. And as t was increasing, we can see the actual path that the curve was taking, or the particle was taking. It's starting right here, and it's traveling along the curve. And it's going in a particular direction. And we want to indicate that particular direction on this. So you will actually see a bunch of arrows drawn alongside the curve like this to indicate the direction that the particle is taking on the path. So we have the path, we have the start, we have the end point, we have the direction. This is parametric equations. I know, it's very exciting, isn't it? Let's go ahead and take out our calculators. Yes! Does anybody need this, though, before I go to my calculator? All right. So, I'm going to go to mode. Remember, mode is right next to the second button. And look for the line that starts with function on your calculator. And notice the second option right next to function says PAR for parametric. We're going to highlight that. And then go to your y equals. What is totally changed? Now we have an x of t and a y of t. What? What is this craziness? So I'm going to go ahead and put those two equations in there. Yeah, go to mode and then change it to parametric. Now, remember that button that you always pressed to get x? Try pressing it now and see what you get. So that's why it's got those other things. It depends which mode you're in. So let's see. Ours was, x was t squared minus 4. And y is t over 2. And then I'm going to hit graph. Now my calculator, unfortunately, goes really fast. So you don't actually see the curve necessarily. And wait a minute. This does not look like we have on our paper. Did yours look like this? Yeah. Go to window. There's some changes in window as well. Notice under window, now it's giving us a Tmin and Tmax before that we didn't have. So remember, ours was going from -2 to 3. You don't have to worry about the T step. That's like how often it's basically plotting points. And I'll go from, there we go. I'm just going to go from -10 to 10 on the Y. And let's try going back to graph now. Ah, that looks more like it now. And mine, again, went really fast, but if you looked really fast, you could see where it started and ended. So there's that. I'm going to show you one more thing with this. But anybody having any trouble getting to any of these things? Uh-huh. All right, anybody else have any troubles? Okie dokie. So one other thing that I want to show you, and if you got one of the fancy color calculators, you got, of course, the color option. But now we have a good use for the, like right in front of X. I went back to my Y equals menu. Right in front of the X, it's just connecting with a line. I don't know if you've ever played with this area over here. I'm just going to hit enter, and it's going to cycle through options. It can make a bold line. So if you have multiple graphs, you could, and this is on the Y equals also. But, you know, if you can highlight different graphs, this is basically its answer to color. But then I have this one, which is a leading 0. It's like got a 0 with a dash, and then this option is a 0 with no dash. Since I'm back here on this one, what's going to happen with the no dash, we'll see the 0. The 0 is like the particle. It will follow the path of the curve, but it won't leave the curve behind because I don't have the dash on. I say, where is it? Wow, that was very unexciting. I think it did it so fast. I'm going to go back to the leading 0. Let's see if we can see it. Ooh. Oh yeah, it happens. It's going too fast on mine. Should be slower on yours though. Do you guys see what I'm talking about? Okay. Yeah. Yeah, it's only on X1. Ooh. Do you want a calculator? Yeah, Sid. You just have to go like to just a regular line. Oh, you did the 0 without the dash? I see what you're saying. That's a good question. How do we force? I mean, what you can do, I believe, but there's got to be a better answer to this. I'm just going to see, when you change the equation, it will force a redraw. Let's see if we change it, but keep it the same. I just typed a 4 over the 4. Yeah, it looks like that's something you can do. Because I saw it really quick pop up there. Any other questions? Yeah. I just went back to the equation and I just typed over it, but I typed over it with the same thing. So but just one thing. Like, I'm just going to type a T. And then it forced the redraw. Any other question? Oh, yeah. Yeah. So there's, my X's and Y's go from -10 to 10. And there is a standard window still for parametric. The x and the y still goes on the standard window, will still go from negative 10 to 10. I actually forget t, if it goes from 0 to 2 pi or negative 2 pi to 2 pi. I'm just going to choose that. Looks like it goes from 0 to 2 pi. Any other questions? Boop. Alrighty then. Let's keep playing with these things a little bit. I'm going to go back to our notes now. Okay, I'm going to give you guys a slightly different equation that I want you guys to draw. You guys try this one on your own. Let me line it up. Sketch. And what you'll see when it's written the other way, it'll do something like, of course it doesn't have to be C. We could call it anything. I'm just calling it C of T. Where'd it go? Oh, I can't even read my own writing. I think that's 4t squared minus 4t. And this time, we'll go negative 1 to 3/2. Eek. Well, let me pause the recording. You guys try this at home. Yeah, I just cut and pasted the table and changed the values of t. Yeah, it ends up making the same thing. So the point of making you guys do this was when we say that the particle, the path of the particle is described by the parametric equations, the path is there, the direction is there. Also, the parametric equations, hidden inside there is the speed of the particle. So the particle is going along the same path. But on our previous problem, let me actually just zoom out a little bit so we can see both. Well, can't see both still. I know you probably can't read it, but you got it on your papers. But we can see the path looks identical. But with the first problem, t went from negative 2 to 3. On this problem, t is going from negative 1 to 3/2. This one is going twice as fast. It's taking half as long to go on that path. So hidden inside there is also the speed of the particle. Well, this first one, even though they're going along the same path in the same direction, same start and end points, that one went from negative 2 to 3 for t, and this one only went from negative 1 to 1.5. So if t is seconds, the top one took 5 seconds. This one only took 2.5 seconds to go along the same path. And we'll be looking at how to find speed, but that's, I'm pretty sure, next class. But speed is hidden in there. Any questions on this? Yeah.
Like, why is it the exact same path, even if the functions are different?
Because, I mean, you can look algebraically and see the numbers, but also, and actually, kind of along this point, it's not exactly your question, but you're going to see that you can have the same parametric equations describing the same curve, which is what's happening here. But the speed of the particle is different. And, I mean, okay, so just a little preview of next class, because it's not that hard to figure out on your own. Speed makes me think rate of change, which makes me think what in calculus? Derivatives. Yeah. So we're going to find that the derivatives would be different here, which is where the speed is different. Because derivatives are velocity, rates of change, but...
Wait, the derivative of what?
The derivative of the top set of parametric equations is different than the derivative of the bottom. So the speed is different. I'm going to wait to answer your question any further until next class, because it is in next class. I think, or is it in today's? Oh no, it's coming up. I take it back. I should look at my notes. Well, let's just jump to derivatives right now while we're at it then. Yeah. Zoom, let's get back. Okay. So yeah, let's talk about speed derivatives. Derivatives. Parametric equations. So derivatives are still going to be dy dx. But wait. We have t. I know, right? Yeah? Nope. But you're onto something. So the comment was we have to add another dt on the bottom. And it's not that. All right, we'll take a look. There's two ways of finding derivatives. So we'll kind of cover something else in here too. Let me actually just put, I'm going to put the dy dt here. So let's go ahead and take this guy, this guy, the first one. X equals t squared minus 4, and y equals t over 2. Don't worry about the interval for t is irrelevant. So we'll look at that. So one way to find the derivative, method 1, is to first rewrite this parametric equation as just an equation in terms of x and y. And that's called eliminating the parameter. Eliminate the parameter. I can't spell. Remember, t is a parameter. We're going to eliminate the t. And so the general way of doing this is... I got these two equations here. Look at those two equations and decide which one is going to be the easiest one to solve for t. Why, yes, because all we have to do is say 2y equals t. Wow, you guys are good. That was easy. And then all I'm going to do is go into the other equation and plug that into t. So instead of writing t, I'm going to write 2y. X is 2y squared minus 4. And that's basically it right there. I'll see if I can sort of, kind of clean it up. So 4y squared minus 4. And wow, hey, if you think about that, doesn't that make a parabola that opens to the right? Ah, what? That's actually also another strategy for graphing the parametric equations is rewriting it by eliminating the parameter and then looking at this graph. All right, so we got that. Now we take the derivative, like you guys know. Now you could do this in one of two ways. We could solve for y, although this one, if we solved for y, we'd have the plus or minus. Let's use implicit differentiation instead. So much easier. So take the derivative of x, you get 1. Take the derivative of y squared, you get 8y dy dx. Take the derivative of negative 4, that's 0. Solve for dy dx, and you get 1 over 8y. Dun, dun, dun. So exciting. So that's method 1, eliminating the parameter. Tongue twister. Say that 10 times fast. All right, yes, Sid.
So the derivative parametric equation dy with respect to dy dt, right? And then here we solve for dy dx, which is changing y times x. How are they the same thing?
Say the first part. How did you start off again?
So the parametric equations have the variable t, right? So we're differentiating. Over here, you've written the derivative parametric equation of dy dt. So I'm learning how that's related to how we solve for dy dx.
So I think this. Let me know if this doesn't answer. So the path itself is on the xy coordinate plane. So when we are describing the speed along that entire path, we want to look at how x is changing with respect, or how y is changing with respect to x. We want to look at dy dx. Now, we can, if we want to just focus on how the particle is moving horizontally, and this is where the use of parametric equations can come in, because for physics applications, sometimes you want to break down something into a horizontal component or a vertical component, and parametric equations does that for us very nicely. So how does a horizontal distance change over time? That's going to be dx dt. How does a vertical distance change over time? That's dy dt. But how does the speed along the whole entire path change? That's how y is changing with respect to x. So that's dy dx. So kind of along that same lines, though, let's look at method 2. Method 2 for finding the derivative, dy dx, is we're going to use the fact that dy dx is dy dt over dx dt. And so we can just take the derivative with respect to time of each component and then just divide those. So I have x and y at the very top of the screen still, so we can see those. So dy dx, I'm just going to rewrite this over again. It's dy dt over dx dt, dy dt. What is dy dt? 1/2. What is dx dt? 2t. Are we getting the same thing? What? It doesn't look the same. That says 1 over 8y. This says 1/2 over 2t. I don't know what you're smoking. Sorry, I didn't say that. Let me edit that out. What time is that? Gotta edit it out at 28:20. All right, so yeah, it sounds like a lot of you guys see it. That's going to be 1 over 4t, but using the work that we did above, we know that t is the same thing as 2y. So if we plug that in, we get 1 over 8y. It just kind of depends on what you're going to do with this next. Is it going to be better to have it in terms of y? Will it be better to have it in terms of x? You can go ahead and put it in terms of x if you need to. Would it be better to have it in terms of t? I don't know. It depends what you're going to do. But yeah, you get the same thing. So either way works. Any questions about that? Yes.
You're saying that the parametric function is helpful, like when determining like horizontal and vertical components of velocity and stuff like that, or not as velocity, like the path. Can you figure out the horizontal and vertical components of velocity using this? Because then you have to take the derivative with respect to a single part of the function, and I know at least the second method wouldn't work.
Wait, you lost me on the end. My mind started figuring. Okay, so
because the
can
second
you?
method is the derivative of the function with respect to x over the derivative of y over x, right? Can you use one or both of the methods to find out like just the velocity of the horizontal horizontal component? Or do you have to like
Yeah,
solve it?
dxct is the velocity of the horizontal.
Gotcha.
Any other questions? All right, so we've gone out of order now of what I had planned. Let me look at my notes real quick and see something. Oh, yeah. Okay. So let's just look at this thing then. Consider this. X equals 1 over the square root of t plus 1, and y equals t over t plus 1. And we're going to look at t just being greater than negative 1. Eliminate the parameter. That is your task. So we got that. Oh, no, I just wanted to eliminate the parameter, not find the derivative. Ah, I got you. Oh, that makes more... Yeah, the derivative would be negative 2x. Good job. I was like, I don't know how we got negative 2x. Yeah, when we say eliminate the parameter, it's literally rewriting it as an equation in terms of x and y. No more t because you eliminate the parameter. Then you could take the derivative of this to find it, dy dx.
Why do we do it in terms of t at all?
Mainly for the physics applications, when you want to break something up into the different components. And the other thing that when you want to break it up into the components, and the thing that's lost here is what's the actual path. We don't know what the direction is. There is one little thing, though. I don't know. Like, compare this to what we originally had. It's a very vague question, but do you think that what we have then will match the parametric equations? Seems like it should, right? What do you mean it won't give us the extra values?
If it's one, well, actually, yeah, for this, it should give you values from negative 1, as t is negative 1 to 0, right there underneath the curve, and if you've got y equals 1 minus x squared, it should just give you the stuff starting at 0, right? That doesn't make any sense. Like, if you plug it into the table, you're going to get more values, but the other one is decided.
You are seeing it. So compare what we started with. Remember we had this graph to begin with? Well, I guess we had this one. This was our first graph. Was it the entire parabola? It wasn't the entire parabola. And then we can see when we actually did this problem, that was the same parametric equations. When we eliminated, over there it is. When we eliminated the parameter, we got this. This is missing the start and stop point. And we have the same thing going on. That's the one thing that's missing with our rewrite by eliminating the parameter. We don't have t to tell us where to start and stop. So you do have to consider restrictions. And we're going to do domain restrictions like we typically do. So if t is going to be greater than negative 1, I mean, where do you think that, what would this graph look like, first of all? If I just graphed y equals 1 minus x squared. Yeah, it's a parabola that opens down. And if we just look at this equation, y equals 1 minus x squared, is there any domain restriction on x right now? Right, x can be anything. You can take any number and square it. Up here, was there any kind of domain restriction? Yes. What was our domain restriction here? Yeah, we have that t is greater than negative 1, which is going to keep this radical positive. But that's also going to keep x positive, right? X is greater than 0. So that'd be the only thing that you want to keep in mind, are those possible domain restrictions. Yes? What? You mean like take this guy?
Yep.
And then, yeah, we could have. Either way, you'll still get the same thing.
Are there any restrictions with respect to y given the ways on t?
This will take care of it. Yeah, the question was, are there any restrictions with respect to y? And no, the x restriction will take care of the y restriction then.
Like, maybe we can assume that it's always integer.
No.
So,
No, so yeah, you got to think about it. Yeah, on this one though, it will take care of it. All right, any other questions? Just got a couple other things, little things. We go until 10:45, right? Yeah, we got time. All right. 35? 45. Hey, Sid, 45? On the pink one, what is 45? Okay, thanks. All righty. We're going to consider these. We're going to do 3 of them. We're going to look at C of t equal t cubed t to the 6th. We're going to look at C of t being t squared t to the 4th. And we're going to look at C of t being cosine t cosine squared t. I'm not going to put any restrictions on t. Therefore, t can be anything. T is all real numbers. First thing I want you to do, eliminate the parameter on all 3 of those. What do you notice? They're all the same. They're all giving us y equals x squared. So are they all going to be the same?
No.
Yeah, probably not, huh? So let's think about those domain restrictions again, because that's where it's going to come into play. I'm going to just set up axes right now on all 3. So, I don't know. I guess we'll start with A. No, let's start with B. What kind of restrictions are we going to have? Now remember, T can be anything. So if we're looking at B, what kind of values can X be? Can X be anything? Sid?
T squared is greater than or equal to.
Say the, so because it's X squared, I just couldn't hear you.
T squared, x is greater than or equal to.
Yeah. Once we square it, it's going to make it positive. It won't be negative. So X will not be a negative number, and oh, look at that. Y will also never be a negative number. So it's only going to be the part of the parabola in quadrant 1 where X and Y is positive. Ooh, I'm still in black. What about the direction? I mean, starting, because there's no restriction on t, so starting at very far negative numbers, going to 0, becoming more positive, what's the direction that this particle is going to take?
You go down the parabola and back up.
Exactly. It's going to come down. Now, the only thing with drawing these arrows, and there's just no way to do it, I mean, which side do we start on? Are the arrows saying start down here, we go up, and then at some point we turn around and come down? I mean, that just seems weird and strange, because we're going to go up forever. When do we ever turn around to come back down? So you have to kind of think about it. It's going to make more sense. We come back down, hit the vertex, and then we go back up. Sometimes you don't know. For instance, let's just go to C while we're talking on that. What do you think my restrictions are going to be for X and Y now? Okay.
Y is between -1 and 1. Or X is between -1 and 1.
Why?
Cosine only goes between -1 and 1.
Ah. And then that, therefore, Y will only go between 0 and 1. If X is only going to be between -1 and 1, but Y is X squared, it's only going to be positive. Exactly. So this guy, it's just going to go along this curve. And he's just going to bounce back and forth. Where do we start?
No.
When t is negative infinity, I mean, where is that? Just la la la, all back and forth. That's all he's going to do. How fun. Think about A. It's the path of A. Yes, Adon.
Why is it doing that? Like, above the line, it's not from like the left and the line to the left.
I don't know. I could have done it the other way. No reason.
Oh.
I just needed to show that it's bouncing back and forth. So I had to show one direction and then another direction. One direction. Sorry. All right, back on part A now. Part A, what are the restrictions? What part of the parabola are we looking at for that one? Yeah, the whole damn thing. This time, x is t cubed. X can be anything then. That's going to make y be anything. Well, y is only positive, but that's the parabola. What direction do we go on this? Does it bounce back and forth too then? Nope. Yep. We're just strictly going in this direction. Yes? Yeah, so when t is very negative, that's going to make x be very negative. So we're going to start over here on the very negative part of x. And as t increases, that's going to make x increase here. So it's going to go in that general direction. Any other questions? All right. The last thing I'm going to do is just give you some helpful things to know, like keep in mind. Some helpful parametric equations to know. If you want a parametric equation A line with slope, I'll just say S over R. The change in Y is S. The change in X is R. Too many letters to keep track of. That goes through the point AB. Then we can say that the parametric equation for that is A plus RT B plus ST. And if you think about it, it makes sense. So when, for instance, when t is 0, we're going to have the point AB. So that's what's going to get us to go through this point. And then from that point AB, for like the next value, let's say when t equals 1, that increases the x coordinate by r, and it increases the y coordinate by s. So the change in y over the change in x is s over r. It makes sense. If you make a table of values, you'll see it. So that's one to know. Another one is a circle. That's a handy one. There's only 3 of them I'm going to give you, and these last 2 are very closely related. Circle with radius r. Let's say centered at the origin. There's actually a couple of ones for this. C of t equals r sine theta, r cosine theta. And the other one is r cosine theta, r sine theta. Anybody have an idea what the difference between these two might be? Direction of travel. Yep, one goes clockwise, one goes counterclockwise. The first one goes clockwise, and the second one goes counterclockwise. That's easy to figure out if you just plug in the quadrantal angles, 0, pi over 2, pi, and 3 pi over 2. You'll see the direction. They actually, I mean, when theta starts at 0, they actually start in different points too, but if we don't consider a starting point for theta, theta can be all real numbers. It's strictly just the direction. And then finally, if we move the center off the origin, circle with radius r, this time centered at AB. Anybody have an idea what we do? Look.
Would you do sine theta minus a, and then cosine theta minus b?
You're on the right track, except we add. Yeah, so this one is centered at the origin. We want to move the origin to AB, so we're going to add A to all the x coordinates, and then we're going to add B to all the y coordinates. So we take all the x coordinates and add A, and all the y coordinates and add B. And again, we could go clockwise or counterclockwise. So I'll just do the first one. A plus r sine theta, B plus r cosine theta. And again, that will go clockwise. You could also add A and B. Maybe I'll put this down just to make sure we know that A is always on the whatever the x coordinate is. So A plus r cosine theta, B plus r sine theta. That's counterclockwise. And that is the end of my story. Any questions? Yes.
Could you go over the value of parts A and B? you got that?
The, like this one?
Yeah, how you knew that? How you knew where to
So we knew to, like just, so, let's do B first. I was trying to decide which one to start with. So think about when t is a very negative number. As soon as you square it, it's going to become a very large positive number. And as t increases from a very large negative number, as it increases to 0, when you square t, it's going to be a very large number, but it's going to get smaller as the magnitude of it gets closer to 0. And then it keeps going. And then for part C, as t changes, like if we just think of the graph of cosine t, cosine just bounces back and forth between -1 and 1. So the x-coordinate is just going to keep going back and forth between -1 and 1. And so we just keep bouncing back and forth. Any other questions? You're welcome. All right, that's the end. I'm going to pause.